Welcome back, calculus students. This is part 2 of the notes for mean value theorem. In this part, we're just going to look at applications and extensions of the mean value theorem, as well as the proof of the mean value theorem. So one of these extensions is the Rawls theorem. The Rawls theorem is a specific case of the mean value theorem, specifically where the endpoints of the interval are equal. So think of a function that starts and ends at the same position, like a perfectly symmetrical quadratic, which is what I'm attempting to draw. Let f be a continuous function over the closed interval a to b and differentiable over the open interval a to b. So very similar setup and assumptions to the mean value theorem, such that f of a is equal to f of b, which is what we have here. Then there exists at least one point within the interval such that the derivative of the function at that point is equal to 0. And you can actually see this in my quadratic. That would be this critical value down here, or the minimum of the function. So the first thing we're going to do is prove the Rawls theorem. So the first assumption is that k is going to be the value that the function starts and ends at. F of a equals, that should say f of b. There are three options, assuming that f is a continuous function over the interval a to b. So option 1 is that the function, the entire function, is equal to k, which means that it's a constant function across the entire interval. And so if this were the case, the derivative of a constant is equal to 0, and that means for a c in our interval, the derivative is equal to 0, since the derivative is equal to 0 for the entire function. Then we get into the two other cases. One represents a minimum and one represents a maximum. So for the second assumption, we're going to assume that there is an x somewhere in the function, somewhere in the interval a to b, such that f of x, so f at that value, is greater than k, the value at the endpoints. Well, if this is the case, since f is a continuous function over the closed bounded interval a to b, by the extreme value theorem that we've seen in a previous lesson, it has to have an absolute maximum. Extreme value theorem, f has an absolute max. Well, according to Fermat's theorem, which we saw at the end of the last set of lessons on extrema, having an absolute max means that f prime of some value c has to be equal to 0. So all we need to do is just let this max be at c. Remember, c is an arbitrary variable. Then the derivative is 0 by, oh gosh, my handwriting just feels like it's getting worse, by Fermat's theorem. Oof. Okay, so 3, it's the same assumptions, except that we're going to identify an x within the interval such that f of x is less than k. And all we're going to do here is just replace absolute max with absolute minimum. Oh, well. So case 1 is just let me just organize this. I did not follow my own note structure. So in 1, you're putting this. In 2, you're putting this. And then in 3, you would rewrite this, but with a less than symbol. And then all of my proof that I squeezed in was actually meant to go into the space below, case 1, and cases 2 and 3. So that was the structure intended for writing these notes. I was wondering why I didn't give myself enough space. That's okay. Let's take an application approach to Rawls' theorem. What does Rawls' theorem look like algebraically in an actual problem? So we're going to verify that the function satisfies the criteria. X squared is a quadratic function that is continuous and differentiable over all real numbers. So we know it's continuous and differentiable over this interval. Then we want to verify that the endpoints are actually equal. So we plug in our -2, make sure you use parentheses if you're using your calculator. And we get that the first one is equal to 0. So when we plug in 0, we better get 0 as well. Good. So we know that f of -2 is equal to f of 0. The function at the endpoints is equal. That guarantees that there is a point between -2 and 0 where the derivative at that point is equal to 0. So we're just going to find it. What is the derivative of x squared plus 2x? Set that equal to 0. And solve. So actually, you know what? I want to change this, so I'm using C. It just makes my conclusion make more sense, keeps my notation consistent. And I'm always looking for consistent notation. So C is equal to -1, and as you can see, -1 is in our interval -2 to 0. And that's how you apply the Rawls theorem. Really make sure that you're checking your conditions. So if this were a test question, I wouldn't be able to get away with just stating that x squared is a quadratic function that's continuous and differentiable. I'd have to write it out because not all functions are continuous and differentiable. For example, an absolute value function would not work because it's not differentiable. So when you go to solve for C and try to take a derivative and try to locate that point, you're not going to get a derivative equal to 0 because the derivative at that minimum point in an absolute value is undefined. So really make sure that you are stating the criteria being satisfied whenever you answer a problem. And that does mean writing sentences at the beginning of your scratch work. Similar situation happening over here. We've got a cubic function which is continuous and differentiable over all real numbers, so I know that it meets the first condition. The next thing I need to check is that the function is equivalent at its endpoints. So I'm getting -8 plus 8, which is equal to 0. Oof, I don't like that both of these examples are 0. Keep in mind the endpoints do not have to equal 0. They only have to equal each other. So this is just a coincidence that they happen to equal 0. And as we can see, f of -2 is equal to f of 2. Next step is to find our derivative. -4, and then we're going to go ahead and locate that C value. And then square root. And if we're fully rationalizing our solution, we're getting that C is equal to 2 radical 3 over 3, but it actually equals plus or minus because we took the square root ourselves. So let's double check that 2 radical 3 over 3 is in our interval from -2 to 2. Go ahead and punch that into a calculator. And so I'm getting that's approximately 1.15. So positive 1.15 and negative 1.5 both have a derivative equal to 0. And there is our solution for C.